the day before the test. So I'll take your questions first. You have questions? I'm trying to be straight about it. Yes.
Do you do a problem with like the DTFT of just a series of numbers?
Go ahead, give it to me.
I'll give you a second.
I'm going to put this down. On the test, I keep getting different versions of this. They say, what are we responsible for? It's basically everything since the last test. But some of the things with Laplace transforms weren't covered on the last test. So the operational amps consider fair game. All right, op amps with Laplace transforms. All right, I didn't ask you anything about that. And I didn't ask you to synthesize anything based on operational amplifiers, capacitors, and resistors. It's probably going to be analysis. In fairness, I'm not going to ask you for synthesis here. So you need to know how to analyze a circuit based on operational amplifiers using Laplace transform techniques. Then, why don't we just go through it? Then you're going to have the DTFT here. And remember duality. So the thing with duality is, remember that you can go back to the Fourier transform properties to get the actual duality for the DTFT. Does everybody remember that? How if we have a P of t, or an X of t goes to an X of omega, small omega, and we're looking for the X of n, capital X, X of capital omega relationship. If that X of capital omega, which will be between minus pi and pi, between pi and minus pi, if that has an exact replica in the small omega domain that is between minus pi and pi, where it exists, where its value is non-zero, and you know what the inverse transform of that is, you can therefore find the inverse transform of the large X of omega to n, X of n. And I'll do one of those just to make sure you're sharp. So it requires knowledge of actual Fourier transforms. That's what I'm saying, the actual Fourier transform to do duality, even though it's related to the DTFT. Everybody understand that? So it's not like you're exempt from all the other things. You have to know the other things to know these things, but the focus is on primarily on the DTFT, not on Fourier transforms. Duality and everything with the DTFT, then the DFT, that's the shortened version of that. Then the Z transform. And with the Z transform, if you remember, we just finished this. We did everything from taking the Z transform, I'm going to do some of this, of the basic functions, right? Then we used properties to get the next in any other information, right? And after that, we did the inverse Z transform. We found out how to do that by simple expansion methods. Does everybody understand that? Knowing the basic pairings that were available to us, you have to know the basic pairs, the way it works. And after that, then we did filter prop. Really what we did is system properties, right? We had an X of n going into an H of n. We wanted a Y of n. We took X of n, made it X of z, multiplied it by H of z to get Y of z, and then did during inverse. Everybody got that? So it's just like what we did with Laplace, right? Just exactly like it. Then we did filter properties. We talked about two specific filters. Really, there was the notch filter, right? And then the comb filter. But we did general filtering theory, low pass, high pass, band stop, and we talked about how they relate to the Laplace transform with the bilinear transform. Does everybody understand this class? I'm trying to just tell you, we just got done with that. This we haven't been on, the early stuff, for a while. Now what was your question? Because you had
Mine was about the DTFS, which you haven't said.
The what?
The DTFS.
Oh, okay, good.
But if it's not going to be in the test, then.
Well, that's part of, you can put that, all these things with the Z transform, really all these things are under that because they're special variants of the Z transform. But the DTFS, what he's talking about is the discrete time Fourier series, when something's periodic. And that's fair game too. I didn't list that specifically. Go ahead, which one do you have?
Series is 18, 12, 6, 0, 6, 12.
All right, X of n equals 18, comma?
12, 6, 0, 6, 12. and then repeats, and 18 from 0.
All right.
Repeats for and
And then it goes back down to 12 and so forth. So first, a smart thing to do would be try to get an actual drawing of this. So I'm assuming this is the 0 point? Did they?
Yeah.
All right, if that's 0, so it's 18 up here, right? And then the next point down is 12. Next point is 6. Really, you can draw lines here. That's going to have a height of 6. And then it goes to 0 here, then back up. And it's doing this, right? 3, 4, 5, 6, that's 0. Does everybody agree with me on this one? I'm just trying to draw it. Now, you can see if you want to do an envelope on there so you can actually see what goes on. It's an inverted triangle, basically what it is. And it will do the same thing back here. So the first thing you do is find the period. Well, what's the period? Well, it starts here, there's 1, 2, 3, 4, 5, 6 terms. Do you agree with me? And the 7th starts again, right? So n would be 6 here, right? Now after that, what we're saying, and I'll try to relate this to the continuous, or to the continuous time Fourier series. Remember before, this will help you. We had x of t, if it was periodic, we could say it can be summed up from n equals minus infinity to infinity of c of n e to the j n omega naught t, and c of n here was equal to 1 over t, the integral from really 0 to t, or minus t over 2 to t over 2. Doesn't matter the integral, it has to be over a period here, of x of t times e to the minus j n omega naught t dt. That was the relationship for the continuous time Fourier transform, right? Now the discrete time Fourier transform has x of n that is periodic. It's periodic. And x of n here is going to be expressible in terms of a summation where n equals 0 to capital N minus 1. I think he uses n naught in the book, I don't remember. It doesn't matter, the symbol is just number. And then here is going to be a constant. You can call it c of k. And then it has e to the j 2 pi over n here. I'm sorry, this is k. K goes from 0 to n minus 1 times k times n. Now, if you look in the book, that should be what he has. He may have a different symbol for this. Does he use C of K in there?
I think he uses x of k.
Is it X? It's a symbol.
It doesn't matter.
All right, what I'm trying to do is let you see the relationship. Here's continuous time. Here is when we basically sample, right, over a certain interval. But remember, it's only over one period. That's the important thing. When we do this, he should have that form right there. Now, then when he has C of K here, he's going to have 1 over n. The 1 over n is just like the 1 over t. What it does is gets the average. It gets rid of that buildup that can happen. It's an average, you might say. Then it's going to have a summation here of x of n here, and it's going to be times e to the minus j 2 pi over n times nk, and n will go from 0 to n minus 1. And that's about what he has, doesn't it? There might be a symbol. He might use an x, not a, he might have a, no, I think he uses x of n, right? Is that what he has, guys?
Yeah.
All right, so now the only thing you have to do is evaluate this for this number range here. All right? And literally, you're going to plug it in. I'll try to do it here. So I know n is 6, so therefore my c of k, in general, the form is 1 over 6 times the summation from n equals 0 to 5, because it's n minus 1. It's just sticking it in there. And then you look down there. Now that's that x of n. And then it's going to be e to the minus j 2 pi divided by 6, which is really pi over 3, right, to the nk power. I'm just doing exactly what the formula says. All right, so the first one you get is C0. If you want all of them, you can get them. But what's C0 just by looking at this? Please, there's one thing you have to see here.
18 plus 12 plus 6.
Well, what he's saying is sum them up and divide by 6, right? It's simply the DC value. I call it the DC value. Does everybody see that, class? All right, so I am all up. What do you get? Just, what's that? Well, I got what? 18 plus 12 plus 6. Let's see. That's what? 18 plus 18 is 36, right? 36 times 2, is that right? Well, actually, what do? I kill this one off, don't I? Yeah. So I've got 36 plus 18, right? So that's 16 times 54, is that right? Is this what he has in the solutions, by the way? Does it do it this way? All right, so that would be the value for C0, right? Now C1, what happens then? Well, I don't want to do them all, but we can do C1. What's C1 going to be here? Actually, C sub 1. Here's where you use the, yeah, that's basically you're going to make use of the cosine or sine or something similar. Let's just write C1 out. It's going to be 1/6, right? Times the summation of 18, right? It's just 18 there. Then it's going to be plus 12. Now here, when I'm looking at this term right here, I have k equals 1. So I'm really looking at e to the minus j 2, or really pi over 3 times n here. This is where k is 1 in that summation, so I'm evaluating. The first one, 18, is times n is 0. Follow me? Next one is 12 times n is 1, right? So it's times e to the minus j pi over 3 plus 6 times e to the minus j 2 pi over 3. And then it's plus 0, right? That's n equal 3 plus, and then we have n equal 4, and we have 6 times e to the minus j 4 thirds pi, right? Plus, and then 12 times e to the minus j, and then it's going to be 5/3 pi, right? Does everybody follow me on this? This would be a kind of a long one to do, but just go through it one time. Now when I look here as far as real numbers here, I have 18 by itself. And do I have anything with 2 pi? I don't get a 2 pi there, do I? So I have 18 by itself. This is 1/6 times 18. Next, I've got this, which is really what? When I think about this, let me do it this way. When I have minus j pi over 3, I'm down here, correct? That's 60 degrees, correct, class? Now, keep going on this. That's minus 2 pi, that's down here, all right? This one, I'm sorry, this one is here. That's 0, that's 4/3 pi, so I go 1, 2, 3, and then that's up here. What I'm trying to do is get some perspective. And finally, 5/3 is here, isn't it, class? All right, now let's see what this coefficient 5/3 is. I got a 12 here, and I got a 12 here at 1/3, so this is 60 degrees, right? This has got a length of 12, this has got a length of 12. Do you agree with me? That's these two I circled. All right, now what do you notice you're seeing? You're taking the projection of this on this axis. The vertical or imaginary portions cancel, and you're simply taking this, the projection here, the cosine of 60 times this, plus the cosine of 60 times that one, or really it's what? 2 times cosine of 60 times 12. Isn't it, class? Plus 2 times cosine of 60 degrees times 12. That would take care of those two terms. Do you all see what I'm doing here? I'm trying to cancel the components out, the vertical or horizontal components. Does everybody see this? Give me a show of hands here, Will. All right. You could make that cosine if you wanted to. All right. But it's easier to see just graphically. Now, this one is at 6 at minus 2/3. Well, 6 at minus 2/3 is here, isn't it? I'll circle this one. And 6 at minus 4/3, well, think about it. Come around. That's 3/3. 4/3 is here, right? 6. Do you agree with me? Now notice when you take the projection of this down here, this is 60 degrees, but it's negative, right? So it's going to be minus 2 times 6 times cosine of 60 degrees. Isn't it, class? What's the cosine of 60? 1/2, right? So the 1/2 times 2 cancels. And really, what you get is 18 plus 12 minus 6, don't you? Isn't that right, class? And divided by 6.
You would get,
Say again.
you would get 18 times, or 18 plus 24 plus 12.
You get 18 here by itself, right?
Right.
Then I've got 12 by itself, right?
The 2,
The 2 cancels because cosine of 60 is 1/2.
oh, right.
All right, so I got 18 plus 12, right? That's 30, correct? And then I have just 6, don't I? Minus 6, right? 30 minus 6 would be 24, correct? And it's divided by 6, agree? It's a bomb. 24 by 6, right? 12 by 3, 4. It's 4. That's for C1. Now, you can see this gets to be long when you got to go through each one of them. I'm not going to ask some of that. I could see that being a 20-minute problem by itself. I mean, if you're not on your game, it might be a 30-minute problem. So I'm not going to ask that kind of problem. Do something with that, will you? No, don't shut the system down. Let's go to the other side.
It's doing the thing.
All right. Is that good enough for you? But I may ask something that requires you to know this and this, even though, I mean, at least understand it, because of duality things, and this, as far as a basic understanding. For 4 numbers, simple numbers, this should be easy. All right, let's keep going. So I put the list up there of what you'd be responsible for. I've got some notes there about things I consider, since we haven't spent much time on it.
I believe you had a question. Somebody had a question.
Yeah, I'm sorry.
The only question I had was, you crossed out that second 18. I just wanted to know why you did
The second one?
It was 18, like you just traced.
Yeah, because that started at 18, right? Right? That's the beginning of the next period. 18, 12, 6, 0, right? 6, 12. Then when it hits 18, it's back to the beginning. So it's a complete period. You follow? All right, I have things written down, but any other questions? Okay, so what I'd like to do, I want to try to do this in a way where we can best make use of the time. First, some basic DTFT Z transform pairings, right? And we'll put both of them down, just like we could put down the Laplace and the Fourier for a given function. So we'll do it this way. I'll start with, if I have simply, let's see, I'm going to start with, this is going to be my x of n here, and this will be my x of z, and then I'll have my x of omega here. We'll see if we can do this fairly quickly. So some basic pairings you should know. If I start with x of, better do this too. The definition of x of z, these you kind of have to know because I may ask them at any time. If you don't know the basic definition to put down, then everything else is for naught. But x of z is the summation from n equals 0 to infinity of x of n times z to the minus n. Now, along with Z transforms, I didn't mention stability, that's implied. When I say Z transforms or Laplace, it implies you understand stability, right? So, without state. And when you look at x of omega, the big difference is what? Where does x of omega start at, class? That's right, minus infinity. And it goes to infinity, and it's x of n. And here it's e to the minus j n omega, right? Now, this, something you need to know is periodic in 2 pi. It means usually if you go from minus pi to pi, whatever it looks like in there, it's going to just repeat itself. Going to keep on repeating forever that way. That's important. This is omega. So keep that in mind. So the basic functions I have is first, delta of n. Now, that's the most basic of all functions you have to know. Just sticking and plugging it into those things, what do you get for both of them? 1. It's 1. Important that you know that. Next function, most basic function. Delta of n minus, in the book he likes n naught. I like a, but I'll leave it as n naught. Now what happens there? Make sure you don't mess this up. When I go to this one, where does that delta of n minus n naught turn on? At? N naught. So it would be z to the? Yes. Over here, make yourself a note. Just let z equal e to the j omega. It'll save you some time. Over here, jn omega. Omega, yeah. Right? N naught omega. All right, those are 2 pretty basic functions, right? You all agree with that? Next one I'm going to do is a to the n u of n. This one we've beaten to death. And everybody should know this in any which way I ask it. A is just a constant. Now some of you probably have thought this through. Could that be a complex number? Yes, in fact it could. In radar it is for some processes. But I want to tell you this, in the real world that we live in, there are no J's. There are no imaginary numbers, all right? However, it is a construct for talking about activity that's got a 90 degrees phase shift in some way, shape, or form, all right? It's only a construct. If I say I have a sine oscillator over here that's multiplying something, and over here I have a cosine oscillator at the exact same frequency multiplying those two, there's a 90 degrees phase shift. And I can, in my mind, assign a j to one of those and call the other one the real value, or call it, it's called quadrature and in phase. One can be in phase, one can be quadrature. But there are no j's in the real world. And I see, anytime I see in the time domain with something observable, like a pressure on a pressure detector or a temperature meter, and they put it's 2 plus J5 is the answer for the temperature. See, that's that's out of the range of even understanding. And if you said that in an interview, they'd probably show you the door. But if you have a to the n u times u of n here, this one without doing it, we should know is z minus a. We can do that if we want, can't we? Y'all remember this? And then you just substitute e to the j omega here. So now we have those pairings, right? These are basic pairings. Something I might add here, if you put a as 0, or a as, add a as 1 here, right? Then this is z over z minus 1, that's u of n, isn't it? Here though, we got a problem, right? Because we have that singularity. Do y'all remember that? Do y'all remember this class, that we have a very odd problem when we had, even in continuous time, when we had u of t, we had to do what? We had to use duality to find that answer. Do y'all remember this? Well, I'm not going to go the whole 9 yards in duality, but duality's powerful because just in continuous time, if you get nothing more out of continuous time, at least right now, I mean, if you don't have a grasp of why this is important, just consider this. If we have u of t is equal to x of t, you'll see the rollover here in a second. All right, now if I wanted the Fourier transform, that's the integral of x of t times e to the what? minus j omega t dt from minus infinity to infinity, right? Let's go a step further. Now, if it's u of t, it just goes from where? 0 to infinity, right? Of e to the minus j omega t dt. Take one look at that and think, just think. What is e to the minus j omega t doing all over? It's just going up and down and up and down. It's a sine and a cosine with an or it's a cosine plus j sine of that angle, right? And you're integrating. What happens if you integrate cosine of omega t from 0 to infinity? Beats me, I don't know. I don't know how to evaluate a cosine of infinity. It's a continual oscillation. This is not something that's understandable. What I'm getting at, the mathematicians spend years doing all sorts of proofs and theories and prove that certain things happen. Engineers just use duality because I know that if I have, let me just show you what I'm getting at. Do y'all remember this here? This kind of situation comes up. These are not defined by the fundamental definition, right? But we get them through duality. How do we know that? I know if I have x of t here, go to x of omega, then I can take that x of omega and make omega simply t, and I can take this here and do what? The 2 pi times small x of minus omega technically, right? Now, think about this for a second. If I have delta t, that goes to 1, right?
Yes.
That's x of t, x of omega. This is how duality works and why it's so powerful, right? Now take my x of omega into the time domain, 1. There's no t, there's no omega, there's no problem. It's just 1.
Yeah.
Over here, what do I do?
Yeah, 2 pi
Delta of
omega
minus omega, right?
but it's like
It won't matter. It's only on at 0, right? Doesn't matter if you have a minus 0 or plus 0. There's 0, 0, 0, 0. All right, and that's delta of omega. Now, what does that mean? 1 goes to 2 pi times delta of omega, right? What is 1? Well, 1 is u of t plus u of minus t, believe it or not. We did something like this, and we proved. Do y'all remember something like this here? I'm trying to show you some. Come on. You remember doing something like this. Actually, the book uses a Sigmund function here. And I kind of made the argument, because of that, that u of t is going to have that delta of omega times pi is part of the, but when you actually look at u of t in your book, you get what? Well, it has a what? 1 over j omega term, right? Plus pi times delta of omega. Do y'all remember this, class? Come on, you do, right? All right. This term comes about from the duality relationship, and I can only tell you that I'm not going to go much further than this, but this is what it is in the time domain. Now, over here, when we get, if you look at your, I didn't even put this down here, but that's not quite true in general. Remember how it repeats every 2 pi, right? So technically what you're supposed to do is not say it that way. What you're supposed to do is say it's equal to the summation from n equals minus infinity to infinity of e to the j omega plus 2 pi n over e to the j omega plus 2 pi n minus a. And the reason you do that is because every 2 pi repeats itself. Y'all remember this, class? Now, I don't care about that form. I care about only what it does between minus pi and pi. All right? However, between minus pi and pi, if a goes to 1, then you're technically, if anybody has your book, look in there, you're going to see this term added to it, plus pi times delta of omega. Can you see it in your books? Class, do you see it? Now, he has that sum, though, doesn't he, in there? Don't worry about the sum crap, because on my test, the only thing I care about is between minus pi and pi, or 0 and 2 pi, if you want to do it that way, over a range of 2 pi. That's it. Now, next, I just wanted to add that in there. This is only if, matter of fact, let me just leave it like this for now. Not worry about that. Now, those are things that we should know. We're going to do something with duality in a second. but there are some properties you should definitely know, and I'll put those down. I'll put one of them here. Anytime we have a function x of n times cosine of omega naught n, or x of n times sine of omega naught n. Either one of these can crop up anytime. And if you look at my old tests, they do. They always crop up in a variety of ways. In x of n, again, it can be anything. This is modulation, it's important. Now, if we do it with z transforms, what happens? Let me do it this way. Better yet, let me go over here. Let me do just the cosine here and show you. So if we do this with the DTFT, this is the one you probably remember the best. It's just like the Fourier. It's 1/2, right?
Yep.
And then it's going to be x of capital omega plus omega naught minus, or plus, I mean, x of omega minus omega naught, right? That's if we did it with DTFT. How many remember that? It's just like the Fourier transform. Got to remember, it's just like the Fourier. That's why the information is so good to keep in mind, to keep flashing your memory with that. Over here in the Z transform, it's a little different. Still 1/2, right? And I don't know if this one's in the book. That's the problem. I tell you to write this down. And then it's, if it is in the book, tell me. And then it's going to be what? X of Z times e to the j omega naught, right? Plus x of z times e to the minus j omega naught. Y'all remember that? How many do? In your book, is that one there or not for z?
It's not.
No? Do you remember me showing you this, guys?
Yeah.
If you look at the DTFT, guys, you have for the cosine times x of n there?
Look at the discrete time for your transform.
The DTFT?
Yeah,
They have, so they have this form in the book?
yeah, I'm pretty sure it's in there.
He's shaking his head, they do. All right, well, I'm glad they have one, but it's the same thing over here, only notice it's z times e to the j omega naught. And that's an important difference, so please keep that in mind. Now, if you do it with sine, what happens? I'm not trying to fly through this, but I'm trying to get through some ground here. Do you all agree with cosine, right? What's the difference if I put a sine down? We're going to modify.
You get a j over the 2, and then you get a negative in the middle. So
You said it, you're right. This becomes j, right? And here, minus, right? All with me on that? Over here, j and minus. That's the difference. Now the thing about these two, the magnitudes of both of these are identical. The phase is different. For the cosine multiplier, it's even. For the sine, it's odd. Remember, yeah, I'm not going to ask too much. I'm not going to ask about phase, all right? But I do want you to know this. So with modulation, which is a big deal, and we haven't done this in a while, here's kind of something I'm thinking about. Just as a straight up transform pair or an operation, I'm going to ask you, you don't have to use just modulation. There's a lot of ways to do these problems. Suppose I ask you to find the DTFT. Let's say DTFT of n a to the n. Now this is a property, u of n times cosine of omega naught n. How would you do it? There's a property I didn't put down. But if you have n times x of n here, assuming you know x of n goes to x of z and x of n goes to x of omega, then over here what happens? I have minus z times the derivative with respect to z of x of z. And over here I have j times the derivative with respect to omega of x of omega. That's if it's multiplied by n. Correct, class? All right, this is a simple property, but I'm showing the property both for z and for DTFT. Give me one second before I get the answer from you. I want to let people think on this. Now, I want you to understand one thing. If and only if you have x of n that is non-zero for n equals 0 or above, got me? If x of n only has values of meaning for n equals 0 or above, then x of z, all right, can be, where you take z and make it e to the j omega, is the DTFT. Or it is x of, I call it omega, the book has e to the j omega. Understand that, class? That's a very important thing to know. So if you have your z transform, if you understand that, and your sequence starts at 0 really, then any DTFT stuff you want, just take z and make it e to the j omega. That's so important to keep in mind. Yes?
Does that say J D omega?
J, this is going to be minus z times the derivative with respect to z of x of z. This is j times the derivative with respect to omega of x of omega. It's the argument of capital X. All right, now the book will have an e to the j omega. Don't put an e to the j omega in, all right? Make sure you, unless you got z, you just replace z with that. But be very careful about making clumsy mistakes on these. I'm just trying to caution you. So this one, back to this one. Now, you know, I'm going to suggest 3 approaches you could do. First, you could say, I know that a of n, u of n goes to z over z minus a. And then I know that if I have this times this, I can get the simple modulation form, right? And then multiplying by n would take the derivative of the whole shooting match and multiply it by minus z. That's one possibility. Do you all see that? One way to do it. Another way, and go ahead.
On your test, would you accept the answer in the form of the derivative? Like,
No, you got to carry out the derivative. Do not carry out the derivative, or you're going to not get a point. You always do the derivatives.
It's only a point.
No, it's all the points of that problem.
All right. Oh, well. Where's that?
You know, I have had in my lifetime, I've done 30 plus years of teaching, and I've had some very comical students, and that have written down some things that just have me belly laughing. But you know, when it says find A, and a kid puts a big A, here it is, and stuff like that. They get these things from grade school humor, but they don't know what they're doing, so they're just trying to make me laugh and get a few extra points. Just saying, they do it. Carry out the derivative. All right, don't do that to me.
Doesn't work.
A derivative doesn't work. What?
I think it's 50 points for the stupid answer.
Now they can flunk either way. It doesn't matter to me how they flunk, with humor or without. But anyway, back to this thing. What's the way you were going to suggest? Because you were ahead of me on that. You were right.
Yeah. No, I mean, I was just going to say that you find A, then you then.
You're going to do that one first, then do modulation. Isn't that what you're saying?
Yeah.
All right, let's make sure everybody can do that one without problem. You all know that a to the n, u of n, from over there goes to z over z minus a, correct, class? Now, multiply it by n. If I have n times a to the n u of n, that means I take minus z times the derivative with respect to z of z over z minus a. And that answer is not correct. You have to carry out the derivative. But that is an actually fair question right there, because it would show that you do understand that. You get credit for some of that. You got to carry it all the way out. What's that going to be?
I think it's something like A, Z over.
Well, take the derivative of the first one, so you have 1 over z minus a, right? And then plus the second one, or first one, z times the derivative of the second brings out a minus 1 here, and I have z minus a squared, right? And then I take the derivative of this, which is just 1, right? The inner part. You all with me? I always do it that way. I look at it as 2 functions. Take the derivative of the first one times the second, plus the second one, derivative of the first. Understand, class?
Chain rule.
That's my way of doing it. There's another way. And then I take this and what? Since the common denominator is z minus a squared, right there, right? And I can see z minus z is 0, and I have an a here. So I have minus a times minus z is just za. And so I find out that this one, in fact, has az over z minus a squared as a transform. Agreed, class? Now if I want the modulation operator on here, I can say this goes to, I know I'm moving quick, I'm going to get out of the way in 1 second. And it's a times z e to the j omega naught, which is just omega naught, over, and this is going to be z times e to the j omega naught minus a squared plus az e to the minus j omega naught over z times e to the minus j omega naught minus a squared. And I've just simply replaced the z with z times e to the j omega naught and e to z times e to the plus or minus j omega naught there plus j omega naught there. Agree, class? Now, there is a form in the book that also says, if I have just, I'll just put this right, you've got this, so this is coming off. There is a form in the book, and a lot of you remembered this, and it's fine to use these forms. Remember, if we had a to the n cosine of omega naught n u of n here, that went to z squared minus az cosine of omega naught over z squared minus, and this is 2az cosine of omega naught plus a squared. That's one form, and we use that for the filter, if you remember, right? And then we had a to the n times sine of omega naught n times u of n. I know you guys, we use these a lot, and this is the form you're probably more familiar with than using modulation to get that. Right? Modulation is fine. You'll never miss with that. But this is just as fine. This is equal to what? Az times sine, right?
Over the same crap.
Over the same thing, right? It's the same crap. How many remember these two? Or at least one of the two? You don't remember that? We used the top one, the cosine one, the filter, if you thought. Think about it, right? Didn't we? All right. Now, you can use those. It's the same answer. It'll give you the same answer. And then what do? Either one of these you take the derivative of, right? There was one thing I wanted to comment on. How many realize the cosine of pi over 2 is 0? A lot of times pi over 2 shows up. How many realize the cosine of pi is minus 1? Remember that. And how many realize the cosine of 2 pi n is 1? 2 pi n. 4 pi n, 1. 6 pi n, 1, right?
Yeah.
Now the reason I'm saying that is because the quiz that I gave you had a cosine of 2 pi n. That is just 1. There's no variability. So it's the DC term. Just keep that in mind. Don't leave the end. We're not quite done here. Last test, there were a lot of people that messed up the duality. You're getting duality again, but you're getting it in another domain, the capital omega domain, guaranteed, without question. It's my promise to you. I'm telling you what you're going to get. It's like I'm throwing a fastball. Bat speed's important. Now that I've said that and got your attention, what could I possibly ask? You might want to stay tuned for this one. So, suppose I ask for the inverse Z transform of, are you ready for this? Omega times P pi of omega. All right, I want the inverse transform. This is a DTFT. I didn't even have a chance to talk about the DFT yet, but where does that go back to? Question mark. How did I do that one? Let's see who's got the $1 million thinking cap on. Go ahead.
The derivative of the whatever pulse.
Why don't we go back to the time domain so that we know what we're doing and use duality? All right? Think about this now. If I had a pulse function of with tau in the time domain, what does it come out to in the frequency? Just small omega. People?
Tau.
Tau, very good, times the sync, right, of omega tau over 2. Does everybody realize that? How many do? How many realize that? All right, now this is like an x of t. Think of it as an x of t. What does t times x of t go to over here? It is?
Derivative.
With a j times the derivative, right, with respect to omega of x of omega. Correct, class? Are you with me? All right. You all see you can take a derivative of that. All right, I'm just going to leave this here. So it's going to be j times the derivative with respect to omega of tau times sync of omega tau over 2. All right, I'm just going to leave that. Now, think now. You use duality. You all see how I have t times x of t. You realize here I have omega times p tau of omega. Everybody see, and this x of t is really what? It's t times p tau of t here, isn't it, class? Now, you all see what I'm going to do? What am I going to do? I'm going to take this p tau of t, and I'm putting it over here, right? And it is going to become small omega first, right? Well, it's actually going to go to minus omega, isn't it? And then it's going to be p tau of minus omega, and the minus omega we're going to turn in, this minus omega goes to just plus omega. Are you with me? You with me? I'm going to make it right now. And what happens? And there's a 2 pi, and then over here what happens? I take the j dd of omega times tau times the sink of omega tau over 2 here, but instead of omega I do what? No, I'm going to leave it as t, right? And then what do I do next? I'm almost there. First, I got to do what? I got to get rid of this minus sign, so I make this minus, make this plus, right? Then I divide by 2 pi. Now, I've got small omega times p tau of omega on this side. You'll notice I have omega times, now I know my tau is pi, don't I? With me? And now I simply take the small omega, make it large omega, and the t goes to n, right? How many see this right here? Now that's duality in a nutshell and in a hurry because I'm out of time. 2 minutes over. Y'all follow me on this. You're getting a duality problem. Heed my warning. Hearken unto me. Oh, they used to do it in England. What do they used to say? Hear ye, hear ye. The herald. Huh?
What did you say that goes
Small omega goes to capital omega. All right. T tau width is pi.
Right. So basically that same thing, but then we're just changing the. So basically just be that same thing, we're just changing the variable.
That's it.
This form.
I had to hurry because I wanted to do this.
I was trying to ask this.
This, you take the derivative with respect to t